All right, hi everybody. For those of you that don't know me, my name is Colin, and I'm going to be showing you how to implement Sokoban in C++. Originally, I was going to show you how to implement Sokoban and do a solver, but that was a little bit overscoped for 40 minutes of typing and talking. So instead, I'm just going to do Sokoban, but to make it a little bit more interesting, we're not going to be using like a vector of characters or a vector of strings or a vector of characters. We're going to be using bits. And so we'll do some bit manipulation, and it should be pretty interesting. But before we get to there, we have to actually know what Sokoban is, which is a pretty simple game where you're this @ symbol of the player, and your goal is to get every block, which is a B, over this period, which represents like a switch. And so the way you win in this case is you just push it over to the right a bunch. In level 1, we do something more complicated where they go all the way down, and then they go over, and then they go all the way down again. And I'm not actually going to solve level 2, but as you can tell, it's a much more complicated level with a lot more going on in it. So the first thing I'm going to do is I'm going to make our main C++ file. Because time is a little bit limited, I'm not going to really be doing a ton of organization of this file, but it's nothing too complicated to figure out in terms of the organization. We're just going to do it all in the main CPP file. And we're going to be using a command line argument for this one just to keep things pretty easy. So I'm just going to do it like that. So we're going to make our main C++ file. We're going to compile it, and then we're going to run the executable. And I'm going to pass in one command line argument. Pretty simple so far. So just to start it, it's like int argc, and then we have char star argv, right? And that's all we need to do to start doing this, just to make sure everything is working before we start doing a bunch of typing. We can always just start off really simple. SD NL, and the one thing we need to do before we start, we try to do that. Right, so now if we do make, you can see we got our hello world. So now we're good to actually start working. So the first thing I'm going to do is something that we just are going to need at some point, which is a point. And I'm going to make this an int x and an int y. I'd rather use an std size t, but at some point we're going to have to be doing balance checks. So it just is going to work out nicer if we just keep it as an int in this case. And the only function that we're going to need in terms of like how to manipulate this point is to add points together. So I'm just going to make a quick little point add function, and it's going to be inline because it's super simple. And we're going to take like constant point p1, and we're going to take another constant point p2. And then what we can do is we can return a new point, because that's what this is doing right here. And now we can use .x is equal to p1.x plus p2.y. And then we can say the y coordinate is equal to p2.p1.y plus p2.y. And that is all we need for that. Let me see why I'm doing bad. That's that. And then we have our inline, we have our point, but that doesn't have a semicolon. Right. So now if we want to see if that's working, right, we can just say point A is equal to 1, 1. Point B is equal to 2, 2, let's say. Super easy. And then we can do point C just to see if this point add thing worked. Point add A, and then B. And then we can do like c.x, and then we can do c.y, and we'll just see what happened when we did that. And you can see we got 3, 3. If I change this to like 10, then we'll get 3, 11. And you can see something's wrong. What's wrong? Oh, there it is. There it is. Sorry about that. Little typo. And now we're all good. So now we have 3 and 11. Good thing we did this little test right here before we started going. So now I want to talk a little bit about what we're actually going to be doing here in terms of like the handling of the state, right? So this is going to be like the Sokoban board state, if you will. And the way a lot of people would probably go about it, we're going to use vector, so I'll just import it anyways, is like a vector of char, right? And then you could say like this is the board, right? And that's a super clean way of doing it. And the only kind of problem with it is you have 8 bits or 1 byte per per tile in your board. And so back to this example, right? You get 8 byte, 1 byte for this, 1 byte for this, 1 byte for this, etc., etc. And you don't really need to do that. So what I'm going to do is I'm going to show you how you can avoid doing that if you want. I do think overall the implementation gets pretty complicated here. So it's not really the best idea in all cases. But that doesn't mean you can't do it, and it doesn't mean it isn't kind of fun sometimes to just get really into the nitty-gritty with these fun little optimizations, if you will. So the first thing is I need to know how many rows and columns are going to be in my board. We'll come back to that in a second. The next thing to do is I'm just going to initialize the player position to be 001 to be 00. And now we're going to get into the actual fun part, which is instead of using that vector of vectors or that vector of strings, what we're going to do instead is we're going to do an unsigned char star for solids. Solids are the x's. Then we're going to do an unsigned char star for the switches. And then lastly, we're going to do an unsigned char star for the blocks. So character is 8 bits, 1 byte. And what we're going to be doing is we're going to be using this to access the actual state of the board. So this is the state of the board. So another way you could picture this is there's a bunch of zeros for blocks, right? And then on this one, did I get that right? Yeah, I did. It's going to look like this for blocks. For solids, you're going to get this, and then that, right? And then instead you get this like kind of, this is what the solids thing is going to look like. For switches, this is going to be a 1 and everything else is going to be a 0. So that is what we're going to be representing in these. It's going to take a little bit to get to there, but that's the goal. So I need another semicolon there because I always forget those. And the first thing I think I'm going to start with is before we actually start assigning all these, we might as well just start actually getting the file and reading it in. And then we can start looking into how to set the bits correctly and how to get the bits correctly. So the first thing we want to do is we're going to use this argc variable, and we're going to actually check to see if we actually got a command line argument that was correct. So the first command line, we need 2 command line arguments basically. So if argc does not equal 2, that means we didn't get a file command line argument from our user. So what I'm going to do is I'm just going to print out an error here. And I'm going to say a path to a single Sokoban level must be provided. Right, so this is kind of my way of making it so I don't have to say you could provide more than 1 level and then it would create a progression or something. We're just going to keep it super simple for this, and then we can just return an error in this case. And you can see a little typo there. And then for now, we'll just keep it simple still. Hi, std or std. I don't really, yeah. So there's that. And now if we do a make, you can see it's okay. If I modify our make file to be like just this, for example, make, and now you can see we get our little error right there. So I'm going to get that away, put this back, close the make file because we're not going to be messing with it for a while. And now the next thing to do is to actually read from it. So we'll create an in stream right there, and we'll name it like file, for example, or level file, why not? And we're going to give it the argv, and we're going to give it the second or first if you're 0 index, which we are. So the next thing to do before we actually try to read it or do anything with it is we want to make sure we actually could read it. So for that, we can just do good, for example. And then if it's not good, then we're going to do another error. So in this case, open file. Yeah, that's fine. And then we'll do this, argv1 and line, and then we're just going to return an error again. So if we do a make, hi, everything is okay. And then if we do this and right, could not open file, and then nothing happens. Just again, this is just like a random thing. Okay, so everything's looking good so far. The next thing to do is actually to read it in. And for this, we're actually going to temporarily use a vector just because it's really convenient, frankly. And we're just going to use it for a little bit, and then we'll be totally done with it. So we're going to have of lines, and then we're going to name that our level. We're also going to use a string when we're reading in the actual level. And so then we can do while get line. So we're iterating through this thing one line at a time. And then we're going to pass it in our level file, right? And we're going to also pass it in. We're also going to pass it in the line. And then we are good to go for a second. Before I forget, it's always good to close your level file when you're done. So let's just close our level file because I should have been closing it the second I opened it. This is where like a defer would be really nice that you see in some other languages, but I digress. And then all we're going to do is we're just going to push back the line we just found. So that's super easy. And now what we're going to do is we're going to actually make sure that everything is okay. So let's just do this, that level is what I named that, and then we'll just print it out. So let's see what it prints out. That can't work, but now that worked fine, and you can see we got our level that we were expecting. So everything's looking good so far, but there's still more to do. One of the things to worry about is we want to make sure that the number of rows and columns is always going to be the same. So there are other ways to do it. For example, if you look at like level 2, right, you see that I added these X's right here just to kind of like make everything a little bit cleaner in terms of the implementation, but technically something like this would be totally valid, and the implementation really wouldn't work for that. So I just added that. So that's something to think about if anyone's curious, like how could you make sure that I'm a little ahead of myself. So we're going to come back to that point actually. And instead what we're going to do is we're just going to make it so we need this. And we'll come back to, if I remember, why we need this in a little bit. So std size t num columns, that's equal to level.size, right? And basically what we want to do is make sure the number of columns is always the same. So we're going to delete that, and then we can do that is equal to 1, I less than num columns. So all we're doing is making sure the number of columns is always the same. In terms of prefix or postfix for like the increments, I just prefer prefix just out of habit, in all honesty, but the compiler is going to put them down into the same anyways, so it doesn't really matter. But regardless, level I.size, and then we'll make sure that these two are the same columns. If they're not, then this isn't going to work. So when we do make right now, we can see we ran into an error. And we're using level 0. So I wasn't expecting an error there. Let's see, function num columns, level I. So because we ran into an error real quick, we can just do level I dot size, and then we can compare it to the num columns. Another way to do this is if you were in a debugger, right? You could just go into the debugger, and then you could just look at the variables. So 10, 10, and then you can see this one is 0 right here. So that to me means that it is getting a second line somewhere. So let's see. Level.pushback, level file.close. Oh, there it is. Oops. I did num columns instead of, which I should have been doing, which was just level.size. Okay. So now we do it. Everything's fine. Everything's looking good. I'm going to keep this assert, but you can see, for example, if I did like levels, level 1, totally fine. Levels, level 2, totally fine, right? And you can see it's 17, 17 and all that. But I also kept those prints around, so now if I did it, that's going to go away. All right, cool. So now that we have that, we have our level, and now what we want to do is we actually want to start implementing the game side of things. So basically the way most games are going to work is you're going to render and you're going to update. And that's really all there is to it. Because we're doing this in a terminal and it's not real time, we have to render at the start too. So I'm going to just do it like this, where there's going to be this state render function, right? And it's just going to take in a state. We don't actually have a state. So let me delete that. Let me make a state. So now we have our state, right? And I'm also going to add a game over function. We're not going to implement this for a while. State update, and we're going to pass it a state. And then we're going to state render, and we're going to do that. So that's our entire game loop. This is our loop. Game loop. We have to render once at the start, just so the update function kind of makes sense. But otherwise, this is our game loop. What we need to do before we actually start running all of these is, one, actually define them, and then two, we need to actually initialize our game state. So I'm just going to make another function real quick, init for initialize from level. Could be a file too, and then you could take all this and put it into one thing, which I'm kind of tempted to do in all honesty, but yeah, I want to do level. No, let's just leave it for here. It's totally fine. Okay, so we're going to pass it in there, right there, and that is it. So there's a bunch to actually implement. State init from levels, and we're going to take a reference to the state in this case, not making it const because, well, we're going to be changing things. The next one is our state init from level. Oh yeah, you actually have to pass it the state too. Sorry about that. So there's that. And then we can pass in the const vector. And then it's made of strings and level. Okay, cool. So there is that. We'll come back to that in a second because I see I have an error there. I'm just going to come back to that in a second. The next one we want to do is our update and our game over and our render. So I'm just going to define our game over state, game over const state, and I'm just going to return false for right now. And I'm also going to fix this right here because you can see I did, there it is. Okay, cool. So now I'm going to get into the next one, which is the update. So this is not going to return anything. It is not going to take a constant state because it could theoretically change the state. Do something later. And then the next one, void state render state. It's going to be constant because we're just rendering. We're not making any changes to the state itself. Do something later. Right. Okay. So now all of this is working in the sense that something's happening, but really if we just ran this right now, this would just cause like an infinite loop. So for right now, I'm going to leave this commented out and we're going to come back to it. But for right now, we need to get into initializing from a level. So when we do that, we need to figure out, actually, that needs to go away. Sorry about that. There it is. We actually need to start doing stuff with bits. But first, we can kind of keep things simple. We know we need to define the number of rows, right? So we can say level.size in this case. because that's the number of rows going down. Our string in the middle of our vector, what our vector is contained of, are the rows, and they define the number of columns. So state.columns is equal to level 0 dot size. And if you remember back when we were doing those asserts right here, this is why we can do the level 0 dot size, because we guaranteed them to be all the same. So level 0 dot size. That is the number of columns. And now what we can do is we actually can start getting to some bit stuff. So I'm going to start with this, and I'll explain it in just a second. So this is the number of bytes we're going to need to initialize state.rows times state.columns. Right, and then we're going to do +7, and then we're going to divide by 8. So as a reminder, the number of bits that go into 1 byte is 8, so 8 bits for 1 byte. We're doing a +7 because we want to go a little bit over just in case. And so that's why there's this +7, so we basically always guarantee there's going to be enough memory malloced. And then what we're going to do is we're going to start mallocing our memory. So state.blocks is equal to, and you notice I used unsigned char star. That's to avoid 1, some weird behavior with signed, and 2, because we're just guaranteeing 8 bytes, or 1 byte per character. Okay, so there's that. Now we're going to malloc it, our num bytes, and that is all we need to do. But because we're mallocing, we don't really know for sure that we're going to be malloced to 0 for whatever operating system we're on. So we actually need to handle that case in case it isn't. So state.blocks, we're setting it to 0 by default. And then for the number of bytes that we're going to be allocating to 0, we're going to do that. Super easy. We have to do this 3 more times, or 2 more times. We have to do it 3 times total. So we did it for blocks. Now we want to do it for solids. And now we want to do it for switches. And this ordering is kind of killing me, so I'm going to put it in alphabetical order. They're the same size, so you don't have to worry about padding or anything like that for that specific thing. Anyways, okay. So what we've done is we've set these, so everything, if we like printed it out right now, we're going to just see a bunch of zeros. So literally just like this, right? And to make the representation work, we need to put 1s in the right place. So we're going to start by looping through the vector of strings that we made. So in this case, where it's going to be state.rows ++ y, and then we're going to do it one more time for, columns ++ x. Cool. All right. So I'm going to get the row so we don't have to keep doing anything crazy by getting it like every single iteration. It also just, I feel like this way is just like a little less bug prone, because if you're like typing out like level y every single time you do something in this thing, it gets a little bit annoying. And you become like more prone to making a simple typo mistake. But anyways, we're going to make a point for where we are. And we can do like .x is equal to static cast int x dot y is equal to static cast int y. So now we have the point that we're at. We could also, by the way, just make it like a point right here. And yeah, why don't we actually do that? So point P, and then what we'll do is we'll just drop this, and we'll do P.y. Yeah, let's do that. That's a little bit cleaner. That's better. Cool. That feels better. Okay, so now what we're gonna do is we have like our point where we are. Just as a reminder, where we are is at the start at 0, 0, and at the end we'll get down to 3, 6. Okay, so what we're gonna do is we wanna go through and see which kind of character we have. So row X, P dot X in this case, right? And then the first case is super easy. It's the case where there's nothing. So in this case, there's nothing, and it's these cases right here. Things get a little bit harder when we get to this, right? What we want to do, sorry, I'm just going to type a little bit so this is a little bit better. And I want to change it so if we have like an unhandled thing, I'm just going to do let's say unknown tile type, and it will just print out row p.x. And then I don't really want the program to continue at this point. So I'm just going to assert false, and the program's going to stop, and it's going to break, which is totally fine for this application. If it breaks, we don't care, in the sense that it's okay that it broke in this case. If it broke somewhere else where we didn't expect it to break, that would be a problem. But if it breaks here, this tells us something about what happened during the execution, and we can probably figure out what the problem was because we can see what the problem was. But anyways, let's actually run this and see what we get. And you can see we have an unknown tile type of the player. And I can actually handle the player really quickly. So let's just do it while I'm thinking. Break, and then its state.player is equal to P. And that's it. But you can see we also have this unknown tile type B, unknown tile type. And then when we get to switches, we'll have an unknown tile type, and we actually don't know how we're going to handle that. So what I'm going to start doing is implementing some helper functions. And I'm going to start with a inline void state set solid. And I'm going to give it, it's not going to be constant. And I'm also going to give it a point. Okay. And what thing you maybe notice is in this case, I am doing a reference, and in this case, I'm not doing a reference. And that's because if I was, for example, doing int x, int y, I would not pass a reference for either of these. And since point is just made up of 2 ints, I'm not going to do it for 2 points, a structure of 2 points. So now we're in this state solid, and you can see we have these solids. And there's a question of how do we actually get the bit at the point? So we want to know if there's a solid in this case at this point in our little bit representation. So the way I'm going to do this is I'm actually going to set up like a another kind of helper function, and I'm going to make it set uChar bit, and I'm going to pass it the state.solids, and I'm also going to pass it the point. I'm actually not going to pass it a point, sorry. And I'm going to pass it the index into it. And I haven't implemented what this state index is, so let's actually implement this. Yeah, size t and state index, and we have this point p function. I'm doing inline. Yep, good. Okay. So because we haven't actually set it up as like a matrix in this case, we've just set it up as a big array, and we're just going to kind of like each row has a stopping point, and then we get to the next stopping point and the next stopping point to go to the next row below. What we're going to do is we're going to return p.y, which is the actual row we're on, and then every row has some number of columns. We've already guaranteed that, right? Because we've guaranteed it's the same size both in our level representation and all the way down here in terms of our assert. So what we can do is we can say state.columns. Did I pass the state? No. There it is. Sorry about that. State.columns. And then we can add the row now, which in this case is p.x. State.index and then state p. Okay. So now what I'm doing is I'm saying I want to set this uchar bit at this index, which is right here, and I want to use this. And I'm using this helper function that doesn't exist yet because we're going to have to do this for blocks, solids, and switches. So now let's actually get into setting a uCharacter bit with what we've actually done. So I'm going to, again, inline, and I'm going to do set uchar bit. It's going to be of typed unsigned, char star. I don't love the name val, but I'm just going to use it. And then we have size t index. Cool, cool, cool. Okay, so first what we have to do is, since we're trying to access this kind of like array, if you will, of bytes, what we have to do is we have to find where our byte index actually is. So we can do size t. We can name this something useful like byte index. And it's just index divided by 8, which is kind of cool. Now we need to find where in the byte this actual thing goes. And again, it's actually kind of easy. We just do this size t bit position, we'll say, index, and then we're doing mod 8. So just as a heads up, you kind of like, I hope I did 8, 1, 2, 1, 2, 3, 4, 1, 2, 1, 2. So I definitely did not, but yeah. So this is kind of like it's going and it's just etc. We'll comment this out just for simplicity, right? So what this is doing is it's using this index to figure out which of these we're in, and this bit position is using the modulus operator to find out which one of these we're going to be in. All right, pretty simple. And since we're using a pointer, we can now modify it so we get the correct byte, and we're going to do bit or. So basically what we're doing is if we're, let's just say we have like, right, if we have that, then the outcome is going to be 1, 0. If I made it this, or equals, right? But we want to actually figure out how to use this bit position to modify the bit position here at this byte to be a 1. Luckily, this isn't super complicated. What we do is we take a 1, and a 1 is always going to be this, and then we left shift it based on where we want the 1 to actually be. And that's all we're doing. Pretty simple. Since we're already doing these and since we're already thinking about bytes, I'm just going to implement the other 3 we're going to need. So if we have to set it, we also need to be able to clear it. So again, index, we're going to need these again anyways. So I'm just going to take those. And the other one we're going to need in just a second is get. So these are the 2 we actually need to. Do I still have these? No, I don't. So there we go. And now we actually need to implement this one. I think this will look a little cleaner. Yeah, let's do it like that. All right, so in this one, we're gonna clear. So in the last case, we wanted to like be able to basically do like 0, 0, 1, right? And we wanted to get from that 1, 0, 0, 1. In this case, what we want to do is say we have 1, 1. We want it to be like this. So our bit position in this case is 0, and we want to change it so that this becomes, that these 2, regardless of whether this is 0 or not, is going to become a 1. So what we're going to do instead of it is we're going to basically invert it. So we get 1, 1, 0, And so this will become a 1. This is going to be unchanged. And these two are going to be 0. So if this was this, we'd get this. And that's kind of what we want. How we can actually do that is we can use and then we can inverse. I don't know if that was super clear. I don't think I nailed that one in terms of explaining it. But maybe the code here will make it a little bit more clear. So we, again, left shift, right? So if, like, for example, the bit position was 0 or 1, we're going to go from like this to, for example, say the bit position was 1, we would go to here. And then we're going to inverse it. So we get this 0, 0, 1. And then we're doing an and equals on this inverse. So say we were doing, let's just say we're doing this, right? And we did an and of these two. You can kind of see we're going to get 1, 1, 0, 1. All right, so that's how we clear. And the last thing to do is we want to get, and I'm just going to be returning a bool in this case. Super easy. In this case, if you recall, actually, let's just see if this makes sense. So in this case, we're going to do our val byte again, byte index, right? And then we're going to right shift it, the bit position. And 1. Okay. So how does this work? What we're doing is we have our giant level, right? Something like that, whatever. Where did I mess up? Oh, no semicolon. Sorry. And there's going to be a certain bit position that we're interested in. In this case, let's just say we're interested in this bit position, right? So what we're going to do is we're going to right shift it, and it's just going to go all the way over there. Right? So this 1, after we right shift it, is going to make it so it's this, but we also will have like some leftovers. So if it's like this one, for example, it'll be like that, right? But then we're going to and it with just a big 1. Not a big one, it's just a regular 1. So when we and together that, right? We're just going to either get a 0 or a 1 because these ones are all going to go away. So we're just comparing these two. So if they are both 1, we're good. And it's going to say it's going to return a 1 or true. Otherwise, it's going to return a false. So hopefully that makes sense. That's bit manipulation. Okay. So now we can go all the way back to our stat solid. And so now we set our uchar bit. And hopefully that kind of makes sense. There's still a bunch of other ones to actually implement, as you probably guessed, because if we can set a solid, right, we also need to be able to get a solid. Get solid, state point P, and then it's return, sorry, we're returning a bool here. Get uchar bit. Right, and we're going to pass the state.solids, and then we're going to pass the state index, state P, and there's that. We need to do this for more than just that, though. We need to do it for blocks. Right? This implementation is exactly the same. And I left that S out right there. So let me go back and fix that. And now we need to do it for switches. So let's go here. Pretty simple, just a bunch of typing really. Okay. So there's one thing you probably noticed that I didn't do, which is that all the way up here, I created this clear uchar bit, but I haven't actually used it. So one of the questions is, if I implemented it, I'm going to use it, so where am I going to use it? So if we go back here, there's only one character or one thing that's actually moving, two things. One, it's this @ symbol. When it comes in contact, it's going to move around, and when it comes in contact with this block, it's going to move it if it can. So that is the only function or the only type of entity that we're representing with bytes that can actually move. Our player, if you recall, isn't using an and, it's just using the, where is it? We're just keeping it simple and just using two ints in this case. So the block though can change, so we need to be able to actually use that. So we're just gonna do inline void state clear block. And then clear uchar bit. Okay, so we've done a bunch of functions that let us operate on our unsigned characters, or pointers to unsigned characters. And I believe that's all we need. If it isn't, we'll come back to it in a little bit. So let's go back to initializing our level. We've just done a ton of work, and hopefully it just all pays off for us. So state set solid, right? Because we're in this X. Let me fix that, delete that, and we're just going to pass it our state and our point, and that's it. So if we do that, we now run into a problem with our blocks. So let's handle blocks. I don't need that, but it's totally valid to use it to like, there it is. We want to break. And now our last kind is this. Actually, I'm gonna do, yeah. Let me do this, state set switches, state p. So now if we do this, we should be totally fine. There is one case that my levels don't handle, but we should handle anyways, which is when a block goes over a switch, it will turn into an uppercase B, or it will once we get to that. So it may be totally valid, for example, to have like a capital B here. So maybe the player has to move something off the switch to make it work. So we're just gonna, we may actually come back. Let's actually leave that in there and we'll come back to that later, if I remember. So in this case, because it is a capital B, right, it is both a block and a switch in this one position. Right, so there it is. So now we have done our entire initialization. We have our assert in case there's an unknown tile type, and everything should be looking pretty good. So what is next? The next thing that I kind of want to do is I want to implement the game over function, because we've just done a bunch of stuff with our bytes. Might as well just finish it. So the game is over when every single switch is covered by a block. So we should see all uppercase B's. The way we can actually implement this is kind of cool. We use our num bytes and we do it's equal to state.rows plus times, plus 7 divided by 8. Yep. And then what we can do is we can do a memory compare, right? And we can say state.switches, state.blocks, and then we can use our num bytes. And since we're using it in this case, we can say if they are not equal, then the game is not over, in which case we should keep going. So we just did a big memory compare. Basically what that means is we say it's like, this is going to return false because, right, not everything is equal. But if we did it like that, then all of a sudden memory compare is going to say these two are equal and the num bytes, right? So pretty simple. If we do it now, we can do make, and we can do this, and we're going to go, before we actually run this, we're going to go into state.update. So for state.update, we're not actually going to implement a lot right now. We're going to come back to it in just a little bit, but we're going to do we're going to ask the user to input something, right? We're going to use a string just for convenience. You could totally use a character. User input, and then we'll use getLine, right? And then just to make everything clean. And that's, actually, let me do it like that. Let me do one more thing. Dot length. So we're going to make sure that the user's only given us one command. And if they haven't, what we're going to do is we're going to just say, oh, I have been doing this whole time I've been typing. ASD. Okay. So now, if we do it, we're just getting input, right? Which is awesome, because now what we're gonna do is we're actually gonna go into the rendering. And rendering is not as interesting as the actual update loop of Sokoban, but it's worth doing before we get into the update because it's just a little bit simpler. So again, we're gonna just be looping through the X, the Y, and the X coordinates. There is another way to go about it, because right now, I'll just show you real quick what we're gonna do versus what would be a better way to do it. Why? But it's a little bit rows plus plus X. Do we need the point for this? I don't remember. I don't think we do. So we're just gonna do it like this for now. And if we want to, we can always just do what we did before and change these X and Y's into a point. So Y less than state dot columns. Oof, that was rough. There we go. Okay. So this is one way we're doing it. The other way you could do it is you could loop through the bytes, right? So we already know, like on our game over, right? You could do this, and then you can do like, right? And then what you could do is you could say like, when num bytes, when I is greater than the number, you basically, where it gets kind of complicated and why we're not doing it basically is if you have like this, and this is a level, right? You could, let me actually add one more just for clarity, right? The actual new line is gonna be 1, 2, 3. That is my dog, by the way, having a dream, right? This is where the new line is gonna be, and it's gonna be the actual like new line in terms of like, this is where the new line is gonna be, but the actual where the byte ends is gonna be like right here, if I counted right, which doesn't always happen. So it gets a little bit wonky in terms of the implementation, and this is just a lot easier to understand, but it is more inefficient. So keep that in mind, but this is just kind of easy, so we're just gonna use it for now. So what we're doing right now is we're checking to see if the y coordinate is equal to the player's y coordinate. And that means if the x coordinate is equal to this player's x coordinate, then we should render the player. So what we can do, I changed my mind. I want to do this anyways. I just cannot make up my mind on that. Sorry, p.y. And we don't need, we don't need that anymore. Okay, cool. Now we are good to actually do this. So if player y right, then what we can do is we can print out the player symbol. The other thing to think about, just because we're here, is, end line. I'm going to put one last thing, sorry, free memory. So let's go back to this definition right there. So we've rendered the player, which is kind of cool, but there's a lot more to render. Now we can use one of those functions we actually just made, is solid, and then we can pass in the state and the position. And then I can figure out where I messed up in just a second. So let's see. Okay, let's see over here. Clear block, flip block, set block, get solid. Oh, oops. I don't really like that naming. Okay. Yeah, I don't like that naming at all. So let me clear blocks. Oh, oops. I don't even know if we'll use this function. We'll just keep it and we'll come back to it. All right, so now state is block. What's the, it takes in a state. Oh, this should be a const, by the way. All of these should be consts. No, set shouldn't, state clear block shouldn't, but state is should, because we don't change it, and state is should also be like that. Okay. Cool, 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 and that should also fix that. Yeah, cool. Because we were passing in a constant to a function that said it wasn't constant, and that created a problem. Okay, so if it's either this or this, we are good. What we need to do is we have to handle blocks, switches, and empty spots. So first we want to check out is if state is block, and we're going to pass in a state. We're going to pass in that. The second one, oh, what am I doing there? There we go. So we're checking if it's a block, and we're going to check if it's a switch. All right, cool. So if is block and is switch, then, right, we know we need to actually render capital B. Now we need to see if it's either one or the other. If it's just a block, but it's not a switch, right, lowercase. Otherwise, if it is a switch, but not a block, let's render the switch. I forgot a semicolon. Else, it's neither a switch nor a block, in which case all right. So you can see we have a problem, and it's because, so let's try again, and you can see now we're rendering, but we're not taking any commands. And you can see it's also accepting more than WASD. Before we keep going, let's see how it handles the other ones. So you can see it handles that. Let's see that one, and it can handle that. So far, everything is okay. We have this, we have this. What we haven't actually talked about is freeing the memory, which I figure we might as well talk about before we get into the last part of the game, state.update. So when we initialize the state, we use malloc to actually create these. And do we actually really mind about this whether we free the memory or not, not really. After the game is done running, the operating system is going to handle it anyways. So it's kind of a waste of time in terms of like the execution. But just to be kind of like clean up our mess, if you will, we can do it anyways. So these are the only things we called malloc on. And you can see there's 3 cases of malloc in the entire program. So we know we're totally fine now that we freed this. If we ran something to check like valgrind, I'm very confident it would return that we have freed up all the memory that we allocated. So last step to implementing Sokoban. And this one is a little bit more complicated because now we're actually implementing the logic of the game. So a while back, I mentioned that we couldn't use size t for the points. And the reason why is right here. So we have our point. We've already guaranteed the user input's going to be 1. So it's going to be like A or something like that, right? We already know we have 1 user input. And in terms of the directions, it can be 1, 0, negative 1, 0, which is why size t doesn't work. 0, 1, 0, negative 1. Again, another case why size t does not work, unfortunately. Okay, so we're going to use a switch. We're going to get the character that our user gave us, right? And now we're going to handle cases. Now, we could do it like this. Let me handle our default case real quick, actually. So in our default case, what we're going to do is we're going to do we can do cout. Okay. We also should stop that from running. Sorry about that. And commands, actually I can just take this. Okay. And user input. Right. So we got our character. If the input is bad, right, we know we have some. That was my dog yawning. She heard the elevator. Okay, so now we have something to basically tell the user if there was an error. And then what we can do is in the case of W, right, it's going to be 0, negative 1. And that's because we're going up in the like actual index array. So if like you picture it, right, you're going from like, if the player was like here, up would be going up 1 in terms of the rows. Right. So another thing to consider is since we're doing like a lowercase w, should we actually be able to handle an uppercase w? And there's really no reason not to, so we can just handle both, and if it's w, it'll fall through to here. So now let's handle the other cases, which is a, and a is to the left, so negative x, right? Break. Now we can handle s, so capital. S is down, so it's going to be 0, 1. We make sure to break, otherwise that would be unfortunate. And then the last one is capital D, lowercase d, and it's to the right, so it's positive 1. Cool. Almost forgot to break there. Okay, so we've gotten our user input. This would totally be a candidate to put into a separate function, by the way, but it's just a little bit easier because if we didn't, then we'd have to handle some kind of return error if the user didn't actually input correctly. So the first thing to do is to update the player's position. Now what you're noticing is I'm not actually updating the player's position in the state. What instead I'm using is I'm adding that point add function that we tested all the way back at the beginning, doing the player, and then I'm doing the direction. And so what we need to do before we do anything else is, even though in here I've defined all the levels to be super nice, so there's no bounds. Technically, we want to be able to be a little bit smarter and just guarantee that if there was a mistake, for example, and we did it like this, if the user tried to go to the left from this position of 0 on the x and 1 on y, they tried to go to -1 on x, there would be an error. An error in the sense that the error would actually be handled. So what we do here is first we check our bounds. So we could do the comment, but since I'm just talking as I go, we'll just skip that. So we do our player pause.x, right? If it's less than 0, or the player pause.x is greater than or equal to state.columns, right? We can just return. Similarly, we can actually just copy that. Right? So we check our bounds. And if it's going to cause the player to go out of bounds, we're just not going to bother with it. The next thing to do is check if the player is going to run into the wall. So the wall, in this case, are solids. So if state is solid, right? So we pass it our state. We pass it the player position. This is our new player position. And if it is going to be a state like that, right, we just return. Otherwise, for now, let's do something that's wrong and see if what we did worked. So far you can see we can't go that way, we can't go that way, we can't go that way, but we can go this way, we can go this way, we can go this way, and now we're going to hit the block, but you can see nothing happened. We can just go through it and we don't interact with it at all. So there's no way to do it, and you can see our command things handling. So now what we want to do is we want to handle the situation where we run into a block. And remember, if we run into a block like this, then it should go this way. If we run into a block like this, it should go down, and you can picture the other two directions, I'm sure. Okay, so we're here, handle blocks. Right, so the first thing to do is say, is it? If state is block, state p, player pause. Because in this case, right, we already know everything. If it's not a block, we can just set this and be okay. Okay, so if it isn't, so now what we're going to do is we're just going to check to see if we run into a block, nothing happens. We can't keep going forward. So far, so good. The next thing to do is actually handle it. So we're running into a block, and there's going to be two situations to handle. There's this situation where everything's fine. There's actually three situations. There's this position where the block can't move because it would be running into a solid. And the other position is like this or like this, where the block is running into a block, and you can't push a block through a block. Some versions will actually allow you to do it in Sokoban, but it's just totally up to you. So if you wanted to do it, you could create like a recursive block thing. But we're going to keep our version of Sokoban super simple. So what we need to do is we need to calculate a new position for that block. So we're going to take another position, right? Point add. And this time we're going to use the player's position, which we know, the new player positions, by the way, right here. And we know this is where the current block is. And we know that it's going to go in that direction. So we can use that. Now, again, we need to check our bounds again. And you can see how this would become kind of recursive because we just keep using this for multiple blocks, because there could be 3 blocks in a row, or there could be like 20 blocks. But because we're making it so you can only push 1 block forward, you can't push 5 blocks forward, we don't need to get into all that craziness. So instead of this position, right, it's going to be Right, so we check bounds for the block. And now what we need to do is, if that's okay, we need to make sure spot is empty for the block. Empty may not be the right word actually. Is empty or a switch. All right, let's actually change that up a little bit again. Is not a block or a solid. So the way we can do that is we can again use our state is block, right? State P. Sorry, block pause. And cool. Else, oh yeah, I'm missing a parenthesis. So just one thing to note here is, you notice like if you go into like state is solid, right? We're going to uchar bit. We're recalculating these a bunch. So if we really wanted to get pretty clever, we could start guaranteeing that we could actually just not implement these at all by using these functions. We could actually calculate them each time, and then we could make it pretty smart. But the compiler may also just catch it for us, where it notices we're using these same things in the same time, and we're using inline, so it should kind of like inline it all together. So there's a potential that it will figure it out and make it so it's not recalculating the same thing every time. Regardless, if we're past this, so if it's not a block, if it's a block or a solid where the block is going to be going, we just return because there's nothing to do. Otherwise, we're in here. So once we do this, we can do state.setBlock, state, okay. So before I keep going, there is a line of code here that's missing. What it is, you may be able to guess, but I kind of want to show you just in case. So we get to here, and what you'll notice is everything looks good. But if I go back, it's still there. And now what's kind of cool here is we can actually test if this line of code is working. And you can see nothing happens. If we do this again, if we run it, you can see everything's fine, but we leave a block behind us. And I can actually start pushing that behind, and you can see we have these like infinite blocks coming about. The reason why, if you want to pause, you can totally pause. I don't, but like, it's just this. We didn't clear the block where we were, and we're not doing it in the actual block pause, we're doing it in the player position. So now if we actually run, boom, 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 and game over, we win. So you can see we actually never tested our state game over, which was kind of bad practice. But you can see the state game over is working. So a.out, let's do levels, let's do level 1. So in this one, you can see we have our capital B. So now we can do it like this, and it's working. And it worked. The last thing to do is we'll add like a so we'll just test that. You won. And now we have a fully working console version, terminal-based version of Sokoban with bit operations. There's a lot that could be made to kind of make it a lot more streamlined, because these things, while they make this implementation a lot clearer, they could be kind of set together, so we're constantly reusing these when we can use them. But that would be a whole nother project, which would take up a bunch of time. So yeah, I hope this was helpful. If you have any questions, feel free to stop by my office hours or email me. And yeah, hope you guys have a great day, and hope the class is going well. Bye.